So yeah, sorry about that. Go ahead.
No problem. Yeah. So just to give a quick background is like this is the regularization methods which can be used in the convolution neural network, or maybe not only that, different neural network as well. So dropout is one of the primary method which has motivated many different methods as well. So in the dropout, what happens? It's basically based on the probability a neuron or the node will be shut off and it will not allow information to pass on. So it showed a very good improvement in somewhere here in 2014, and people have widely used it. Earlier, it was meant for the CNN, but then it showed a great accuracy and improvement in the network for other network as well, basically other algorithms as well. Now the next is a drop connect. So what is the difference between a dropout and drop connect? Is in the dropout you're shutting down the node and stopping the information flow. But in the drop connect, you are not completely shutting down the node. But instead of that, you are shutting it down the partial number of the incoming connections. And due to that, like your node will partially remain the active. So let's say if there are 10 incoming network connections, so out of 10, basically your 5 will remain active, 5 will remain inactive. So your partial information flow will go and it will basically allow the network to move forward. In the third one is a special dropout. In the special dropout, basically what happens, your entire channel will be blocked to move forward. So basically in that case, like you are not dropping the neuron, you are not dropping the particular connection, but you are entirely dropping the feature space itself, the channel itself. And based on these different methods, like many other different regulation method has been implemented as well, like shake and from shake connect or many more, but then I'm not going deep into that other methods. The recent one from the Google is the DropBlock. So we'll go further like what the DropBlock is and how it is more effective. So over here, you can see the picture of dog and generally like this is what happens in the dropout. Like when you apply a dropout, that means like your pixels will randomly shut off, maybe like that information will not flow. But the problem is like the neighboring pixels are carrying the same information. As an example, if you are shutting down any pixel from the ear, it will still allow you to move forward, like the other neighboring information pixels will carry the same information. But instead of that, like drop block concept is like, okay, let's not allow the feature itself to move forward. So as example, like here is the sample mask. I'm not going too deep into the algorithm, but if it is a like sample mask and there are the basically two pixels which we want to shut off. So instead of shutting down the pixel itself based on the block size, which will be a parameterized number, just block the entire block size. Let's say if block size is 4 by 4, then 16 pixel will be shut off. So that will block the entire feature to move forward. And another parameter is a keep probability. Sometimes it says keep probability, sometimes it says a drop probability. So that means if it is a drop, then it is 1 minus keep probability. And when you pass this keep probability, the algorithm computes the gamma behind the scene and block the features, basically the area within the images. If we keep the block size 1, that means it's equivalent to dropout. And if we keep the drop size higher, which will cover the entire space, that means special dropout will be the feature which will entirely block your channel. This improved accuracy on the ResNet 50 MOBA latest like state of architecture basically, but it did not show any improvement on the C510, which is but obvious, because if you increase the number of block size, it will just block the entire image and it will not come up with anything else. And if you keep the less number of block size and less number of probability, it will turn into the overfitting. So that's the one of the problem with the drop block when using it on the small segment data set. Now, what is a data augmentation method? So generally data augmentation comes into the picture when basically you have less number of samples and you need to generate a more samples. At that time, data augmentation comes into the picture. So what are the different methods in the data augmentation is like a random horizontal. So if you see the pictures over here, like this is the picture, it's in the horizontal flip, it is something like this. So during the training process, it will randomly like just take the images at the time and turn into the horizontal flip and add basically another image. So in the vertical image, it will be like vertically flip around the image will be. And the random crop will be like, in case of your image, like it will just take the portion of the image and resize it and zoom it, like something like this. And basically it can be any portion of your image as well. The rotation is like some, this is a vertical rotation, but like it can be anything between 0 to 360 degree. You can rotate your image and pass it to the training network. At the same time, like you have to multiple options, like after rotating an image, how you want to keep your image, like fully expanded portion of that or resize or something. And another is like a RandomErase, which just recently introduced by in 2020 or so. What happens in that, like it basically solve the problem of occlusion in the image. So what happens, like here it's an image. So during the training time, when you pass the image, the RandomErase is like a parameter free, but at the same time, it gives you capability to pass the parameter as well. Either it can be a size of the scale or the probability, depending upon what number of parameters you want to pass. So what happens, like when you use RandomErase, it basically cut the portion of the image, and then after that the new image will pass to the network. So it can be either square, it can be a rectangle, it can be like size can be anything. Like you can control it by the parameter, but it's not required to do that as well. So after passing through the random image, there are two different options, two different operations can be possible. Either image will be changed or image may not be changed. So if changed, then it may be like arbitrary size of the rectangle will be placed on the image, and that area will be replaced by many different options. You can control that as well. It can be like random numbers between 0 to 225 depending upon your image. If it is a gray image or maybe like color image, you can control that. In case like sometimes you can pass into 0 numbers or the 1 numbers as well, and sometimes you can pass it with the mean value of the imaginate data set, which is by default within the algorithm. And let's say if you want to control it with some other things, so you can also do it. But again, like it's a parameter free, that's what the main purpose is, and you don't need to play around a lot. So what happens like on the RandomErase, like when the original author, they claim that it helped to improve the accuracy on the CFAR 10 and CFAR 100 data set, but like it is on the ResNet 50 and ResNet 110 architecture, and it took more than 300 approaches to get to beat the baseline architecture with their baseline accuracy. So now in this, like we see like two different problems. Like dropout, it is very good state of art. It shows the improvement on the ImageNet 1K data set and 224 by 224 images, but did not improve on the small segment images. Here, RandomErase, it shows the improvement on the small segment, but it takes like a 300 approaches to reach and beat the accuracy, and the very deep network architecture it took basically. It's computationally heavy. So in my new approach, like what I'm suggesting is like we can combine these two different approach in a controlled way, so that we can leverage we can basically get a little higher accuracy compared to the baseline architecture with the help of RandomErase plus DropBlock, and with the controlled number of occurrence of the regularization versus and the data augmentation method. And I compared it with the three different approaches. One is the baseline approach. Another is like throwing it a more number of augmentation method, just to make sure like adding a number of augmentation doesn't help it. And I want to prove it like it doesn't make sense. Like you increase the number of probability or increase the number of transformation or augmentation, it doesn't help it until unless you have controlled architecture. And the third is the DropBlock, which is the random with the random image, which is my proposed approach. So just by DropBlock and random image with the controlled number of transform, basically controlled number of occurrence plus controlled probability for the small segment, it helps to improve the overall accuracy plus the number of reduced overfitting effect. So this is my baseline architecture. So the reason for this complex architecture is I just wanted to make sure like my baseline accuracy is not so simple or not so low. So what I did is like I just try to recreate the VGG16 architecture on my own, and here when I was implementing it, like I did like some of the changes in the baseline architecture. So I just had the horizontal flip by default in the first place, and then the 2 layer of 64 size of convolution layer followed by 128 and 256 intermediate max pool layer when I going for the higher size. Then followed by 512 6 layer with the max pool in between. The original VGG16 is using a dropout, which I do not wanted to use it over here. So I changed and implemented a DropBlock over here in this network, and then the fully connected layer of the 512 nodes. So another thing I have changed over here is like the original has a 4096, but then I just need like 10 classes and 100 classes. I reduce it to 512, that number of fully connected layer. Kernel size same 3 by 3, stride 1 by 1, padding 1 by 1. Data set is, these are the 3 data set. All this data set, CFAR 1000 is a 32 by 32. MNIST has been rescaled to 32 because its original is a 28 by 28. These are the parameter settings, not going too much deep into the parameter settings, but then it has been tested on the 100 approaches. MNIST has been tested on 15 approaches. Tesla T for GPU, Google Probe, Collar, and parallel computing has been basically leveraged. DropBlock range is 2 and 3 because the 4 is too much higher and 1 is a dropout effect. Drop probability has been 0.4 to 0.1 to 0.4 incremented by 0.1. Random rotation is 0.0 to 90 degree. We can go further as well, but it's sufficient for this. Threefold cross validation did not. So basically here I did not leverage the default training test set, but instead of that I just mixed both of them and then created a training set and test set as part of the full validation, and then take the average of accuracy, and then random erase scale 5% to 20%. Coming on the result set, like what happened, like when with my baseline architecture on the CFAR 10, so 87.865 is my highest accuracy I received with the drop probability of 0.2 and the drop block size of 2. And with the drop augmentation probability is 0.3. That was my baseline architecture, accuracy on the CFAR 10. And when I took these two different things as two different parameters as a fix basically, and see like by adding a random erase and other random augmentation method, does it help me to improve the accuracy or not? But then I realized, okay, no, basically I found that with the random erase, with the same setting, with the two different augmentation probability, it beat the accuracy 88.345, 88.37. So that's up to 0.51% accuracy has been increased. And when we throw the additional transformation augmentation, it just brings down the accuracy. That means like, along with the random erase, if you keep on adding the transformation, it doesn't help it basically, or if you just throw your number of augmentation, it doesn't help network to improve it. Similarly, like in the MNIST, it was a different one. MNIST, the baseline is a very good at 99.13 within the 15 epochs. Drop block size is this one, and the probability is a 0.2. But when I compared it with my proposed approach, it just went down 95.217 and 96.28 with the random erase. So in this data set, it did not help to, my approach did not help to improve it. And now going on the MNIST, so CFAR 100, so CFAR 100, it does help like from 55.915 for 0.4 drop block probability and 2 as a block size. And when I apply the random erase on top of it, that means 57.24 up to that, I got almost 1.32% higher accuracy compared to the baseline architecture. And if you see the data augmentation, it's a 0.3 and 0.5. It's a two different data augmentation probability that give me a higher accuracy compared to the baseline one. Okay, so these are my experiment. I did a lot of experiments earlier, so to make sure like I'm at least trying, I'm getting like the best baseline accuracy and then testing it. But here in the results set, I did not include all my experiments and just covered the what are the relevant experiment, and we can showcase what has been achieved. In the next slide is like CFAR 10 and CFAR 100. Like I used cross entropy loss over here and measured for the 100 approaches how the loss is going. So if you see over here, like for CFAR 10, it's continuously going down. The trend is going down. That is so for the training set, and for the testing set, it's also basically loss is going down. And we do not see any effect of the overfitting or increasing basically the loss or anything. So from this, you can see like the also at the around 65 or somewhere, we see like there is a stagnant in the loss. We do not see like further loss over here. And it's the same like in the terms of the accuracy. This is like we can see like the 65 or 70 epochs are good enough. Not we don't need a 300 plus epochs compared to that. Similarly, in the CFAR 100, we see like around 70 epochs. We get the best accuracy, and we do not need to go computationally heavy like 300 epochs or something. It may like we can test it, but then due to time limitation and the computation, it looks like this is sufficient. At the same, like the graph is going down instead of like any kind of sign of overfitting or anything. Now moving forward to the conclusion is like the approach which I presented is like using of the DropBlock plus random erase with the control number of the occurrences and the probability. It helps to improve the accuracy, and it helped up to 0.5 to 1.3% improvement compared to the baseline. And that also in the multi-channel. So we see like CFAR10 and CFAR100 is a multi-channel data images, and it did not help on the MNIST because it's a single channel data set. So basically like this approach is effective on the color images. And the part of the future work, like I tested this approach on the small segment, but the same thing can be tested on the higher segment images as well, 224 by 224, all the custom images. Second thing is like I have leveraged like a kind of VGG16 backend architecture, not completely, but did some alteration modification, but the other state-of-art method can be also tested. Networks can be also tested over here and see like how it performs as a part of the future work. We can also, like when we are testing at the higher number of basically other networks with the higher resolution of images, we can try to put the multiple drop blocks in the network and see like whether it helps with the random images. That's also as a part of the future work. And second thing, and the last is like, which I basically realize is recently is like, if we have 224 by 224 image, we can resize it to the smaller image, fit that into this approach and in the basically architecture, and we can save on the computational as well as we can save on the timing and can get the better accuracy as well. So that is again a part of the future work. Like we can see like how the 224 original size giving the performance versus like the reduced rescale size image gives the performance. That's all a kind of my part of the future work. So that's all, I guess. Yeah, these are my references during the project. Yep, that's all. Thank you.
Perfect. Thanks. Thanks, Bob. If everybody can go ahead and, if you can, turn your cameras on, and we can all and unmute yourself, and we can all give Bob a round of applause. So nice work. And yeah, so I guess I'll go ahead and open up questions to the floor. Just go ahead and unmute yourself and ask your questions.
Just a quick question. How did you decide where to put the DropBlock regularization?
That's a very good question. So it took me like almost 4 to 5 days of effort and to see like I tried many different combination, like all. It's not possible to try all the combination, but what I did is like I tried to put at every max pooling layer initially. I also tried to put at randomly 2 or 3 block size and drop block in the layer as well. I did not test it through the entire image, but I run it for the 20 epochs and see like how it is performing. So initially when I was developing my code and trying to fix my baseline architecture, so I did lots of initial experiment to figure out like what is the best place to put the drop block. So now what was happening actually, so if I put the block in the beginning, the information was flowing and stopping over there. And at the same time, if I increase the number of blocks, drop block within the network, it was dropping too much information. So the best accuracy I got it when it was at the end and before just a fully connected layer. So that's where I decided. Of course, like does it cover all the experiment? No, because it's like endless number of possibility, like a number of drop block you can put it at 5 different places, combination of multiple places, 2, 3 or something. But based on like my time and the possible, like what are the basically I can try. I did like 10 or 15 different combinations and then decided on, okay, this is giving me the best baseline accuracy.
Nice, interesting, thanks. Well, and just another one, what was your training, like your experimentation setup like? Because it seems like you went through a lot of different sessions with a lot of different data sets.
Yeah, so when I did it first time, it basically initially I implemented on my local machine, and it took almost 2 hours of time. It did not give me any result. It was keep on running. So I did it on the Google Colab, which took almost 40 minutes of time on the GPU, T4 Tesla and similar level. Then I upgraded myself on the professional version, but then still it was not helping me much. So what I did is like I created 3 different Google accounts, including on one Google account, 4 different execution at the same time. So I was running a 12 execution, almost 8 to 12 different execution at the beginning to see, and even after that as well. And it was running over the nights. In the professional edition, like it doesn't have a limitation of 12 hours window. So it was helping me at least like a parallel computing plus multiple Google image. Trust me, like at the end, Google asked, they did not give me GPU. They realized like I'm consuming a lot of GPU, and they stopped my access as well for 4 hours. I spent another $10, another Google account, and then start executing it. So it was like a painful journey, to be honest.
That's intense. I was running into the 12-hour thing on Google Colab as well. Yeah. Thanks.
Trust me, I spent like $40-50 on Google Colab Pro. At the same time, Kaggle. At the same time, I was running on the Kaggle as well, the different experiments. Because like if I go back over here, let's say these are just my some of the basically experiment I'm showing it over here. But when I'm running it, it is like a many different augmentation probability, DropBlock size, and the other things. So which I did not include over here, but it's not possible to run it on the single session or 2 or 3 sessions. So that's why like I ended up spending money to make sure like what I'm doing it covers at least whatever I can cover in 2 or 3 weeks of time.
You guys started figuring out how to beat the system. Just create more accounts.
Actually, I also used initially EC2 machine because EC2 machine we can go up to the as high as possible, but then it was burning out my money, and I didn't want to use my professional office version of EC2 machine to avoid myself in the coming into the management eyes like where he's burning money. But that's why like.
I feel like don't they give that to you just for free to play around?
Yeah.
They mentioned that there's an EC2 program or Azure or something for EP students, but yeah. I couldn't find out how to use it.
Exactly. So through after that office hours, I think the second last office hours, I actually went back. Like at that time, my experiments was going on, but I went to the Azure as well for that to get the higher capacity and the more number of sessions. But it was not free, even with our Johns Hopkins account as well. But the Kaggle is free, but not like what the experiments we are running in this.
I guess maybe I'll piggyback off that last question. So I guess you were comparing to the baseline that had DropBlock, and so you had this kind of process that you went through to tune where to put that. Where then was the RandomErase popping up, and how did you tune kind of the best location for that?
So RandomErase, like what happens like when you are passing through the 100 epochs in the training time, let's say, when it is going, so random erases will be exactly at the input layer, just like a horizontal what are other transformation you are doing. Before you feed it into the network, you make sure your image is occluded and then feed it into the network.
Gotcha. Yeah. And now that as soon as you said it, I was like, oh no, I remember that now. Can you go more into, I guess, like what is the, so you mentioned the occlusion problem, but I guess I don't know that I know the formal definition of what the occlusion problem is, and I guess why on the data sets that you chose, should we expect that that using RandomErase should then help? Like, what are the occlusion problems in those data sets, and why should they?
Actually, you got exactly the same question which I had when I was reading through the random erase paper. And they mentioned about this problem, and they also use the CIFAR data set. But that paper did not help me to understand what exactly the occlusion they're trying to say. But what I understand at the high level is like the what they are saying is like rather than you pass the images as it is into the network, just do some kind of blockage in the images, so that the network will not learn your images. So basically completely, instead of that, every time you run your epoches, or not epoch, right? Every time it goes into the network, a different image will be presented to the network, even though it's the same, but it's a different version, and the different kind of block or the rectangular is cut out. Not cut out. Cut out is entirely different thing, but it's occluded and then it passed into the network. But yeah, you're right. Like that original paper did not help me to understand much into that what exactly occluded they are referring to.
Yeah, I guess one way to think about a lot of these data augmentation methods is, on one hand, you're right that like we don't want to learn the data, and so there are certain operations like the random crop. I think is kind of the best example I can think of. That it's like an artificial way of increasing the small and finite sample size that you have. But another way that some of the other operations like random flip. That those are, and even random crop to some extent, that they're introducing some type of invariance into the representation that the neural network is learning, so that, for instance, whatever representation that you're learning, it is invariant to random flips or rotations, so that I mean, in some sense, a convolutional layer should be rotation variant just by what they are, but there is sort of this I don't know, issue of having a finite sample size. So it's like this weird like interplay, I think, between invariance and like smoothing that kind of can happen between the two.
Actually, you brought a very good point, and I did, like, before even I started a project, I was just trying to learn this how the CNN works and these other things. So what I observed is like if I'm passing images to the network, the original image, and what accuracy I get, and then if I keep on adding the transformation, it just start dropping the accuracy instead of improving it. Like and in the 95% and most of the time, like more than 95%, I see like it doesn't help. Like even though like these methods are very popular, but it's not help. It was not helping, at least me. And then I did like some random search over the net, like what wrong I am doing. But then I realized, okay, this is what the problem is. Like we need to be very cognizant when we are using a transformation, and that's why like okay. Now I realize the problem with the DropBlock, because it's exponentially. It goes exponentially. If you have 3 size of block, it will just block the 3 by 3 9 pixels. If you go 4, then immediately it will jump to the 9 to 16. So it is like exponentially blocking it, and it's not helping on the small segment. And then I realized, okay, this kind of combination, or this, if I use both the features, which works as a data augmentation, but actually works as a kind of regularization also, you can say. So 2 different regularization in the single network, then it should help me for the small segment. And that's why it triggered me from your, basically what your original question is.
Yeah, this is kind of like a maybe the first, I guess, obvious question to ask is when you saw that drop off, did you go back and look at the training plots to see that it actually converged? Because I wonder if it would have a longer training time. It's is one of the reasons why you could that learning this more robust representation may just take longer time to train.
Yeah, so for you're saying like for DropBlock only with some probability, did I train it for longer epochs?
Or I mean, when you added those extra 2 operations,
Yeah,
and
that
saw
means,
that big drop off in accuracy,
yes.
that I wonder if another issue, which is I guess you could call it another regularization method, but early stop, that may perhaps the the algorithm hasn't I guess trained to convergence, and maybe the early stop was sort of preventing.
Yeah, you're right. In fact, yeah, in fact, like out of my curiosity, like I actually run it for 300 epochs for different combinations. what I noticed is like when I add like multiple augmentation method or maybe like some other experiment, most of the time, like after 40 or 50, it doesn't go beyond it. It just very minor improvement beyond like 50 or 60. That is what my observation is. Most of the time what happens, like it's funny, but like if I add like two drop block or drop block with two different augmentation method, boom, it doesn't go beyond 22%. Irrespective of if I run it for 100 purchase, but like from 20 purchase to 100, it just take it over 22%, 20%, 15%, 30%. So then I realized, okay, like adding a more number of obstacles or the dropping the features, it just doesn't help me. I need to be basically very cognizant, like what I am dropping, what I am adding, and what I'm passing it.
Yeah. Another issue is, I guess perhaps some of the networks that were chosen. I've used some of those networks in the past and have had a hard time. Like those training plots, they're pretty erratic, you know, in terms of like bouncing up and down. And so I've even watched like accuracy on those. They more or less will follow loss to some degree. Some of the ones that I've seen that have a smoother training profile are like ResNet and SqueezeNet. That operation of having learning on the residuals for me in the past has really helped.
You're right. You're right. I tell you the reason why it is not smooth. And to be very honest, like this is from what I just had the last, I was running out of the time. And from the last result, I picked up that training loss after the execution and plotted. But when I take, if I would have taken the multiple purchase and then take out the average, then it would be a smooth, like if I go over here, sorry, where I'm clicking. Oh yeah, so it is a very jaggy kind of ups and down, but like I did not take the average of multiple execution or duration because I was, to be honest, like running out of the time after not many experiments and then putting it down my all the findings. So, but definitely, if I would have taken the multiple
and money.
Money. Yeah.
There's only so many runs you could do before you're in the bank for.
Yeah, so then it would definitely would have given me a much smoother graph if I consider the many thing, consider many execution and then smoothing it out, taking the average of it. But at least we can see the trend over here. This is from the one single, but trend is there. So that was my main thing to show it, like at least not aligned to what I was expecting basically.
Yeah. This is maybe one of my more interesting questions, but I don't know. Have you heard of variance or variable relevance propagation? So it's kind of a way of like asking the question of how much did a variable have on the impact of whatever class it was classified as in the classification case. And what you can get out of variable relevance propagation with convolutional neural networks is you can kind of trace it back to the original image to then have like a heat map for what parts of the image were used for that classification. And so it's kind of this way of like, I don't know, getting some explainability out of neural networks because they're just like this black box. But it occurred to me, as your experimentation is really about a lot of these different like augmentation methods and regularization methods, that I was thinking that perhaps using variable relevance propagation would give you a visual tool for understanding precisely what these operations are doing, because you could do something on the original baseline model, do that variable relevance propagation, add in RandomErase, for instance, and you can go back and see like, well, how did that affect the types of heat maps that I was getting back using variable relevance propagation.
Yeah, this is really interesting. So honestly, I did not get a chance to go further in that direction, and it did not even heard about basically this area, but I will definitely do some kind of exploration and see. But when I was working on this project, one thought came in mind, which is very much aligned to what you are saying. Like, let's say this is the image, but in this image, actual important area is maybe a portion of this. So the thought is like how we can identify the most important portion in the image, and then just in the subsequent epochs pass on in those areas and try to train the network. So it will help us to reduce the number of epochs if we just concentrate on that particular segment of the images.
Yeah. So like on this, I was sort of like asking this question about like how, or in my mind about how, like what is the occlusion, what is being occluded in, like what is the occlusion problem in like the CIFAR data set? When those images, it's like a centered object, the thing that you're wanting to predict is like the thing that's in the center of the image. And so to me, like the occlusion problem is like, well, maybe I'm interested in something that's behind something. And so if I add this like a random erase modification on the front end, then some of the images are going to have that thing that's kind of affecting my classification. That's going to have it blocked out and help learning that a little bit more. But I thought about it a little bit more, and I thought, well, maybe in circumstances like the CIFAR data set, it's not that there's something occluded, but rather the CNN, whatever gets learned, maybe the algorithm is actually focusing not on the thing that it's classifying, but maybe things around it. So like, for instance, you have a plane here. I think that it probably is from CIFAR, if I recall. There's planes as a class there, but there's a background that is the sky. And I wonder if like, if you were to do variable relevance propagation on that, if like some of the pixels that is going into the classification is actually the sky. Not to say that that's a bad thing, right? Because, you know, there being a sky there, well, it's going to tell you maybe it's not a building or I don't know. The problem is that there's sky in a lot of those images, right? So, but maybe like the frog, or you know, there's probably sky in like the horse, because you know there's always a sky in the background. But maybe like it sort of prevents using that operation will help prevent
Right.
things in the background from being influential.
Yeah, I think like even my thought process is very much similar to what you are saying. Is in the original paper, like what they meant is like if they keep on blocking the different portion of the images during the training process, ultimately at one point of time, network will identify, okay, which is the most important, or like what is the background color and what are the object in the network, and then probably focus on that. So because like in the first epoch, this area is, let's say, blocked out, then the second epoch, this area is, let's say, blocked out, third epoch, but then ultimately, like after the 100 different executions or multiple executions, probably it will realize, okay, this may be the object which is classified as a plane, and then just ignore the rest of the information. But yeah, it was a difficult time for me as well, like how they are addressing this in the original paper. And in fact, they also use a CIFAR 110 data set as well. But that paper was mainly focused on how they come up with the algorithm and basically a result set.
Yeah, I would say as a side comment, I don't think I made this comment about using variable relevance propagation, but I've looked into the implementation of those, and I think they actually get pretty tricky, especially when you start, because you have to kind of like go through backwards through the network to calculate these influences that a variable can have. And so operations like dropout, and I imagine block dropout, which is a newer one, you have to sort of like define ways of doing that. And I suspect the research is new enough that I suspect people maybe haven't done that yet. So as far as implementing something like that, I wouldn't suspect something like that would necessarily be doing.
But it will be definitely interesting area because like in the images, like most of the time, the actual object will be like very much, or the actual information is very much condensed, and the rest of the information may not be relevant to what we want to classify. Yeah, I agree.
Yeah. Well, I might have dominated a little bit of time there. I jumped in maybe earlier than I thought. Are there other
It is definitely interesting area, and yeah, it's basically a good amount of effort as well as like patience required when we work with the computer vision programs.
Yeah, yeah. There's kind of an infinite amount of flexibility you have when building networks, and it's important, I think, to figure out exactly what
Why
the
to put
method
it?
to the madness is. People seem to add one thing here and there, and it's always hard to figure out. I think, well, what exactly you
Yeah.
saw a benefit in this case? Why exactly was that? Is always a murkier, harder story, I think.
Yeah, in fact, my guess, this is my just guess estimate. Like right now, I did a try and error with multiple different combinations, but like when actual CNN architect people, like convolution network architect, they must have some kind of methodology or some kind of math behind the scene to exactly decide like where to put what are the components, what will be the size and stride, because otherwise like it is a million billions of different combinations on the network and it's impossible to try and test it out. So, but I think that will be the entirely different subject or maybe a PhD level computer vision.
Yeah. Yeah. And often the feedback you get, if you're just looking at training plots, it's like, okay, this one did worse.
Uh,
It's hard to get that good feedback to tell you exactly what a network is doing. So you have to have like a lot of intuition about the operations and think about what they're doing for you in a given problem. It's like some of these operations I start thinking like, well, what exactly are they doing on MNIST, for instance? Like I've always been astonished that CNNs can even do well on MNIST anyways, because everything's already aligned for you. So like I think
exactly.
CNNs are really good at doing like textural, like representing things texturally, but I don't know. Maybe I think LeCun's like interpretation of like we're just giving you building blocks and then we're going to create some distributions later on by
Right.
allowing you to piece them together.
Yeah. So NIST is like a I would say like it's a first step when we are learning a CNN a vision algorithm. That I realized later on, like okay, CNN is sorry, MNIST is a pretty easy data set, and there is no point to test it out. But then I already tested it, and that I tried to see like if the MNIST fashion is helping me or not. But then it is again the single channel MNIST fashion is the same 28 by 28. I ran it for 20 purchase for one single, and it just boomed 99 point something accuracy. Okay, I said like there is no point to go further in this direction. and then in the over enthusiasm, I try, okay, let me take now the 1K, imaginate 1K data set and see like how the network is performing. And it's a 224 by 224 images. And it basically like I realized within some time, like it's no way I can test it within the timeline. So that's the reason I put it to 224 in the future. But one thing is sure, like when you have like a black and white images, like if we add this approach to black and white images, it just start dropping the information because it has a either 1 or 0 two different times, or maybe like a very gray and white, like two different pixels in the network, or sorry, in the images. And if you start dropping it at the multiple layers, then probably the network won't learn. Otherwise, like it will end up into the learning well if we pass exactly the same training set. Second thing is like, yeah, they have like a default training and test data set. So I was like curious, like what was the reason for giving the 650K in the training and 10K is as the testing? Like basically, what's the reason? Like, can I go and combine and then do it? Does it make a difference or not? But I think it did not. Basically, I would not say did not make a difference, but it was a good experience. Like at least I was able to implement a threefold. I wanted to go for fivefold, but time.
You'd be in that much more money. But yeah, I think yeah, there are those like fixed training test splits. They're just for reproducibility, but hopefully with a image database that size, hopefully there shouldn't be any difference between what you're doing. Doing some cross validation accuracy is kind of another
So
way of reporting generalization error.
got it. Yeah, so I was just curious, like maybe the distribution on the training set may be the different and the test set may be the different. That was just my guess assumption. And
people will do that to you on like Kaggle competitions. Sort of have those differences and sort of there'll be this expectation that you'll sort of try to embed some robustness or invariance to things in your analysis as kind of the I think the secret sauce of winning those competitions is actually being able to incorporate some of that sort of tools like RandomErase that I imagine is incorporating some of that type of invariance.
got it.
Cool. Are there other questions out there? I feel like maybe I didn't give people a chance to actually ask questions.
Hey, Paula, I was interested in asking about the results section. There was a portion where it said NA, and I thought, what was the score? Was it just like it was too low to grasp anything?
No, it was not the reason. I'm happy that you get this NA very quickly. It was some issue in the execution time, so I did not get the result.
I see. And then the other thing was, I mean, what we've talked about, what do you think was, so essential where I see the blue highlighted in the data augmentation of RH and RE, and those outperformed, the different segmentation of RH, RV, RR, and RE. Like, what do you think made it just perform that much better?
It's a very good, interesting question, and I really thought about it, like why this segment made a good improvement and not this segment. So basically, this is like aligned to what my hypothesis is. Like in the small network, small images, like DropBlock has a limitation. Like it can either drop 2x2 block or 3x3 block or 4x4. 4x4 is pretty high for them. So that's why like RandomErase will fill up the gap in between. That's my hypothesis. And basically random horizontal flip is by default is a part of my baseline architecture. Reason for that is actually it was as a part of the baseline in the DropBlock paper. So I wanted to match it. Now coming back to the additional transformation like random horizontal, vertical, rotation, and erase. So my guess estimate is like what is happening, like drop augmentation probability is, let's say, is going to 0.2, 0.3, 0.4, 0.5 higher and higher maybe. Then there is a high chance like all the transformation will be executed, augmentation will be executed, and it will do a multiple operation on the images, which in turn like it will end up into the multiple images for a network, and it's not able to learn all the different variations and combinations.
All right, no, that's very interesting. Thanks, Pallav.
Yeah, it's a good point. Some of those you're going to have it rotated and flipped and reflected, and yeah, I guess there's so many different operations that could all happen at the same time, and eventually, what left do you have to
It's, yeah, it just a network end up in like, okay, what should I do with these different things? And another thing is in the random rotation, I kept the expand false. So because of that, what happens like when the image is rotated, majority, not majority, like a 20 to 40% of the image area becomes a blackout because expand is false. So it tried to fit the image within that 32 by 32. So if your image is like this, and if you flip it, then and try to fit it into the same size of the block, it will resize the image, and then rest of the area will become a black. So it doesn't make sense for a basically network to learn that black area, or maybe like the image will be too small for them, and then on top of it like this regularization and the augmentation will drop the further information. So that is another reason as well.
Yeah, it's a good point. I suspect if you just tried to, because the random vertical flip in there isn't wildly different from the random horizontal flip that's in the other ones, but really the one that's categorically different. And as you said, realize it was full, like the continuous version of the rotations where you would get those cutoffs. So if you are losing some information when it blacks out, but it's interesting though that I think that's evidence that whatever CIFAR or whatever the neural network is doing, it may be learning from those pieces that are getting cut off. Right. Instead of just focusing on that thing that's in the center, that's the image, that it is maybe some of the grass and some of the sky that's being learned.
Yeah, and in fact, like if you have a bigger size images, like and good computation capability, it will be a good experiment to see like how these come out when we have like larger images, and we go with the high number of epochs. Probably it may give you like a better result compared to what I get, but still like it will be interesting. Like, so overall point is like we need to be very cognizant when we are adding what transformation and what are the additional operations and augmentation we are adding in the network. Is it helping it to understand the network images in a much better way, or it just creating a confusion or kind of multiple different images with the same label? So that's where like my main approach is like, okay, rather than you just throw your additional augmentation or additional transformation, just be very cognizant and see like what is helping the network.
Yeah, other questions out there? Okay, cool. Well, let's all thank Pallav again. So yeah, thanks.
You all.
Nice work.
Thank you for joining. Yeah. Cool. So